afternoon. It's my pleasure to introduce as our first speaker Unzicker from Munich, who's speaking on evidence.
Hello, thanks for coming. My talk is on evidence. We need new criteria for evaluating scientific results. And as Isaac Asimov, I believe in evidence. That means if I should believe something, there has to be evidence. The question is, if there is evidence, do I have to believe everything? Remember that fossil records back then were taken as evidence for the existence of land bridges. And Albert Wegener in 1912 was ridiculed for his idea of continental drift. A famous geologist of the time said, if we are to believe Wegener's hypothesis, we must forget everything which has been learned in the last 70 years and start all over again. Sometimes that happens to science. And another example where something went wrong in history is Otto Hahn's research on transuranian elements. He was producing actually evidence for these transuranian elements, and Enrico Fermi even got the Nobel Prize for this wrong theory. So, and of course, the standard textbook example of a wrong theory backed by evidence is the epicycle model of medieval astronomy. And Julian Barbour, in his book, The Discovery of Dynamics, he made a beautiful collection of observations that directly backed this model that were taken as evidence for the model. So, the obvious lesson to draw here is beware of false knowledge. It is more dangerous than ignorance. And we must question our current knowledge of science as well. And I think a good candidate for this possibly false knowledge is the standard model of particle physics. And I know your reaction now. You say, okay, we know that the standard model of particle physics is not the ultimate truth. It's an approximation. Okay, maybe there is somebody who thinks that it's wonderful, it's perfect, it's intellectually appealing, it's the ultimate truth. So presumably this talk is not for you. But I think the majority of you maybe would say, well, it's okay, it works, at least it describes the data. So it's the best thing we have, so let's continue the work. But there are lots of deficiencies of his model, and you have to look at history. Were the land bridges really something that preceded Wegener's theory? No, they were a dogma. Did Otto Hahn's theory of transuranian elements, did it really advance science? No, it hindered progress. And of course, geocentric astronomy was a wrong way that hindered progress rather than advancing it. Was the Copernican revolution just an improvement of the epicycle model? No. It all went to the junk room of history. And this is why we have to question our current models. So some people might say, okay, so there might be, the standard model is fine, there might be a replacement theory which is even better, as it was in the case with Newtonian mechanics and Einstein's relativity. But sorry, this is an offense of Newton. Okay, this is not the relation. The relation is rather epicycles relates to Newton like the standard model would relate to a theory of everything if there is any one. And there cannot be done a better service to the truth than to purge it from things spurious. I think it's very useful to look at history and they also the philosophical convictions of the people who had really some findings in history. So, but the question is, if the whole model crumbles, I mean, with which concept we are left? How do we distinguish undeniable facts from fallacious evidence that backs a model but supports the wrong concepts? Where to draw the line between the really established facts and questionable evidence? And I think there are very few people who might agree with me where to draw the line between these two concepts. So I would prefer to talk how to draw the line, and also to look at the philosophy, methodology of physics, at the history. A scientific theory clearly must be falsifiable. I think this is elementary school of scientific methodology, okay? But nowadays, unfortunately, we have also people who do without elementary school of methodology, chaotic inflation, SUSY, symmetry breaking. And there are also people seriously discussing if we ever can do scientific methodology without, in the absence of empirical data. So I think doing science without empirical data, that's pre-Popperian, that's a kind of kindergarten of scientific methodology. And scientific methodology in the absence of empirical data, I think this is a joke. And the much more serious problem, now we're going to the serious problems, is unscientific methodology in the presence of empirical data. And there is a lot of so-called evidence which really does not deserve the name. There is a crisis in physics, despite there is a lot of so-called evidence. And there's a lot of course, empirical data and observational data. But we must look at it knowing about history of physics, methodology of physics, and also philosophy, natural philosophy. And I think the main reasons why physics is on the wrong track is it ignores history, it ignores philosophy, it ignores methodology, and also sociology and psychology, which is also very important. So obviously, I mean, why could one suspect that the epicycle model was wrong, even before Kepler? Because it is a very ad hoc system of postulations, a complicated model with unjustified concepts, and there were people who are aware of this. If the Lord Almighty had asked me before embarking creation, I should have recommended something simpler. This is King Alfonso el Sabio. And I think physics shouldn't ignore its history, and this is part of the history of physics, and it also has to deal with philosophy. Because if you do physics, you want to understand, and you have an idea how the laws of nature possibly can be. So we are interested in understanding, not just introducing more parameters and fitting data. And one important thing is, I think, the simplicity. If a theory is not sufficiently simple, it has no chance to be true. This was also Einstein's conviction. And we should not neglect these philosophical ideas which are at the root of our understanding. Truth is found, if ever, in the simplicity, never in the multiplicity and confusion of things. And if you talk about philosophy, about these philosophical concepts underlying our understanding, of course, there are important thinkers who expressed themselves about methodology, and everybody knows the structure of scientific revolutions by Thomas Kuhn. He described in detail this particular sequence of an anomaly which is not explained, then a free parameter gets introduced, And with all these extra free parameters, the model becomes increasingly more complicated. And this is a sign of a scientific crisis. And what we observe today, not only in the field of particle physics, where we have hundreds of free parameters, but also increasingly in the standard model of cosmology, we observe this increase of free parameters. So I think there's a lack of methodological reflection in physics. And I would just like to list some methodological fallacies. It's just taking a few examples. Neglect of the hard facts, theoretically wishful thinking. There's always a signal interpreting non-evidence, and the model is compatible. What does that mean? Newton said God created everything with number, weight, and measure. And if you look at today's physics, there are some very important questions which are just left out of the debate. I mean, why is the ratio of the mass of the proton and the electron 1836? There is no explanation for this. Why is the fine structure constant 137? So we walk around these very important questions, and we fail to predict really the very basic properties. Okay, the standard model cannot predict masses. Nobody explains the basic concepts, and it's also not realized very well that even if you have observations, if you have results such as from CERN, there is an entanglement of theory and experiment. To a large degree, experimental results consist of theoretical assumptions. So it's a co-evolution of theory and experiment, and sometimes theory has taken like 99% of that so-called observational result. So we tend to interpret relatively banal observations as exotic findings. For example, the Higgs boson. The evidence for the Higgs bosons is basically 2 photons, okay? But everything decays into 2 photons. So if you have a complicated model, it's very easy to arrive at such conclusions you like. A very good treatise of particle physics, I highly recommend these 2 books, is Andrew Pickering's Constructing Quarks and How Experiments Ends by Peter Gallison. Well, I really would like to go into detail, but we don't have time here. These are really, really excellent descriptions of experts in the field of particle physics. Pardon me?
There are many, many more channels than just the 2-photon channel for Higgs boson.
Okay, I am happy to address that in the discussion. Yeah. Then you have there is always a signal illusion. I mean, you do excessive filtering, triggering, and background removal. And of course, I mean, if you take away all the newly discovered so-called particles, there is always something that is left over. And you always have a signal that can be interpreted in the desired way. Cosmology, unfortunately, is on the same way. And I think this is a methodological fallacy. And we also tend to interpret non-evidence. I mean, if you get all your data just from 4% of the universe, and you juggle around in distributing the dark energy and dark matter and various other free parameters, it's very easy to fit the data to the desired model. And well, you often read the model is compatible. A talk postulates with a possibly unlimited number of parameters is not something that works on the long run in science. And yeah, I should not forget here a very important element of Wegener's dismissal was that he was ridiculed as a non-geologist. He was a meteorologist. So people were saying back then, oh, he's not an expert. How can he express an opinion about geology? Okay? So Harry Collins, I like very much his books. He says, if you're honest, almost everything you know is hearsay. Even if you are a physicist, even if you are an expert in your field, most of what you refer to is hearsay. And you might phrase it also less politely. We all parrot. I also parrot. You parrot. You parrot. And unfortunately, you have to parrot. Because being in the scientific mainstream is the most natural thing, and it's very painful to leave the comfort zone of scientific consensus. Once you leave the comfort zone, you pass immediately from the expert to the idiot, okay? Because you're not agreeing anymore. You're not knowing, so to speak, certain things. And why is this a problem? There is evidence for this. If there are 5 people around you who claim that the length of x equals the length of a, you would agree. This is evidence. There is evidence for this behavior. And it's much easier to make such statements in science. So the problem is, once you stop parroting, and everybody has to parrot, it is terribly difficult to evaluate scientific results if you alone have to do it. And it's also very easy to go wrong if you do not parrot any longer. There are 2 serious dangers. If your reasoning is based on wrong concepts, your lifelong efforts in science might be useless. But on the other hand, if you're going to verify the entire history of physics, every result, we will probably not achieve a new result in your lifetime either. So the question is, first, we have to overcome contemporary groupthink. A few words of encouragement. In the sciences, the authority of thousands is not worth as much as one tiny spark of reason of an individual. The intellectuals make ideologies out of their theories. Unfortunately, also in physics, many ideologies exist. Who does not follow the fashion easily drops out of the community members which are taken seriously. That was Sir Karl Popper. Few are able to calmly pronounce opinions that dissent from the prejudices of their environment. Most even are incapable to ever reach such opinions. And Louis-Victor de Broglie, who said about the founding fathers of quantum mechanics, if one had taken the ideas of these scientific geniuses, who have been the promoters of modern science, and submitted them to committees of specialists, there is no doubt that the latter would have viewed them as extravagant and would have discarded them for the very reason of their originality and profundity. So, we are again here. I believe in evidence, but okay, what is evidence actually? What should we consider as evidence? And how to separate the really indubitable facts from fallacious evidence? And I think we need new standards for establishing scientific consensus. Clearly, what is not the right thing to do is what is not sufficient is the publication in a scientific journal. There are lots of examples where completely wrong things have been published, and so on and so forth, and important discoveries had been rejected by the journals. Agreement of all experts, as in geology in the 1930s, is certainly not a criterion. Established within a field, and I mean that's a so-called community of physics, that's typically a closed environment, and everybody outside is considered too far outside the field to be allowed to have an own opinion. Your best friend is convinced of it, he is maybe more knowledgeable than you, but this is not an argument. All this is not sufficient, so what can we do? I mean, gravity, okay, it's like this. This is our own perception, but it's very, very rare, and you can't do this. Like Archimedes, I would say, if something is established in college level, very basic experiments, you can do at home, you can do in college. So there is no reason to doubt it, okay, if something is established in this way. So we're not debating this. And if something has gone to technology, it's also clear that it works, okay? I don't doubt the photoelectric effect because every digital camera works with the photoelectric effect. It's clear that Einstein's general relativity has a time delay, because otherwise the GPS system wouldn't work. Okay, so we see this working every day in technology, and I wouldn't doubt the existence of electromagnetic waves, because there are mobile phones. Okay, there are millions of proofs every day, and well, unfortunately, also nuclear physics works to the point that nuclear fission works with the atomic bomb. Okay. So you couldn't argue about that, about things like that. But an important criterion, I think, is if we have access to the raw data and can verify this. So I don't doubt the cosmic redshift, because I worked with the data. Okay, you can download millions of stars and galaxies with the redshifts of the Sloan Digital Sky Survey, and you see how the data is processed, and you can verify every step in between. But this is not the case in most of the big science experiments today. And for example, if you compare CERN with SDSS, there is an important difference in structure, because you have so-called independent groups, CMS and Atlas, working on different detectors and claiming they are verifying. But what they are doing is a vertical work from the bottom, the detector science, the triggers, the hardware analysis, the programs, and eventually they end up in claiming that they have a Higgs boson, and the other group does the same. But what we need is a horizontal structure. So every group has to publish its results. There should be an independent group which only works with detectors, and another independent group who does only the software. And every group at every stage has to publish its results without judging it in a certain direction or in a certain model, just to publish it, to document it. And so everybody is free to enter the stage wherever he wants. If you doubt that electrons exist, okay, go to the raw data. If you doubt that another thing exists, okay, enter that stage of the model and you can verify it. I think this is the testability and reproducibility of science we need. And there is some hope that the internet, of course, will bring us to that point. Unfortunately, we're not here, we're not there. So to summarize, the new criteria would be own perception, which is very rare, college level experiments, application technology, verified by different independent fields, public access to raw data and analysis. And here I want to go a little bit more in detail. There should be something like the World Scientific Heritage Open Data. We need original experiments, okay? It's not sufficient that something has been published in 1961 by Hofstetter, okay? Why don't we repeat everything? We should repeat this very basic experiments of particle physics and put it on the internet every day. Of course, we need the raw data. It's not really useful to have a paper of 12 pages in a physical review that claims the discovery of a new particle, because nobody understands it. I doubt even the experts do understand it, but certainly not anybody else. And we need that horizontal analysis that makes transparent this process. Okay? You have to back up this data, you have to store them permanently. That holds also for astrophysical experiments. You have to document it very well. Of course, it's not okay if you have millions of lines of code in the software of processing the particle physics experiments and nobody documents it, that a general educated scientist can follow it. Okay? So, sometimes there is the need of data reduction. We need to concentrate on a subset of the data, but in this case, this has to be an independent subset, not influenced by the assumptions of the model. We need openness. We need all the data on the internet. We need calculability, not only the data, but also the programs. You should run these data. You should be able to run this data. this is a true version of reproducibility, and we would also metadata and support. I think this could be the future of new standards in scientific evidence. And, well, you find a couple of these ideas. Well, I could talk about applications, but I'm afraid there's not enough time, so we should leave a couple of minutes for the discussion. There are a lot of results you could discuss under these aspects, under this criteria. And, well, you could read some of these thoughts in my books. Bankrupting Physics, this is the English translation of Vom Urknall zum Durchknall. And this is another book in Hansa, and this is a book about particle physics, a part that I recommend, Pickering's book. And this is my last book about Einstein's idea and also his philosophy of science. Yeah, thank you for coming. I think we need new criteria. Thank you for listening.
Thank you. So we have a couple of minutes for questions.
Yes, I've done particle physics analysis basically all my life, and I don't know any community which is so open and so honest about the data. For example, DAISY is now publishing the original or providing the original data from the Hera accelerator to the public for similar reasons, just because nobody should have a doubt about what is being done. Yeah, and also at CERN, we have many different groups. Every year we educate new students to be able to analyze data from Atlas, for example, where I'm working. And it's new people coming in, it's groups from all over the world, from India and Pakistan, and a lot of people which have maybe different ideas about physics. And everything is open and honest there. Mm-hmm. I agree that, of course, we don't have the Einstein yet, who is able to put all these puzzle pieces together to one simple theory. But your arguments, I have some problems with that. If you say there were people saying there were length between the continents, mathematically this is equivalent to the idea that these continents drift apart. It's the first step to the right theory. Yeah, and these EPC cycles, if they reproduce the data, that's the first step to understand the mechanics behind it. And the same way, the standard model of particle physics, it has hundreds of predictions which are all checked, and all the analysis and all the data we are looking for have been invented 10 years ago when the apparatus has been built. And now each of these predictions came true. And there's hardly any physics model which is so well tested as a standard model of particle physics.
Mm-hmm. That was a long comment. You're right that the model is called well tested. I would recommend that you read all the very good tests of the geocentric model of astronomy in Julian Barbour's book. And but maybe the important point is the one you started with. You said you're an open community and you're a honest community. I don't doubt that. I even think you're doing your best. I don't doubt your sincerity. I just think that as a whole and involuntarily, you are fooling yourselves about the capability of understanding all this very complicated model. Because there are so many different groups and you are just unable to transfer this knowledge to a common body. So, to summarize, I don't think you do not do your best, that you're dishonest. But the problem is inherent. I think this is a problem of big science and big groups and paradigms. And if a certain amount of money and a certain quantity of people is in there, it's very hard to go back. And to your comment, I mean, if you think the land bridges are okay, if you are happy to work on the land bridge, it's okay for me too. Yeah.
So you were next.
Yes, you said you were that we're unable to process or to really interpret the amount of data that certain experiments generate. Well, supposing you would make all the actual raw data freely accessible, how would anybody without the computing power that you have at CERN would make any sense of that?
Yeah, I waited for that. But I heard this many times, but I think it's an excuse. So it's okay, you produce so many data that no computer can reasonably handle. But whose fault is it? I mean, just particle physics grew to a nonsensical complexity with amounts of data nobody can reasonably handle. But whose fault is that? Okay? And if you can't handle the CERN data, why put you on the internet the HERA data? Okay, you say you're working on that, but put also all the programs, all the documentation. I would be happy to look up the collisions of the HERA, of the DC in 1978. I would be happy to see the Gargamel data. I would be happy to see Hofstadter's data on the internet. Why don't you do that? That costs the air conditioner of the CERN. It costs nothing. We want this very simple, transparent data of particle collisions on the internet, and no particle collision at all is transparent available at the time. And I think this is a scandal, because CERN invented the internet, and the last people who are making proper use of it is CERN. Okay?
So we have two more speakers, then unfortunately I think we have to close because
very interesting talk, and the question for me as an experimental physicist is, if the cosmologists say they only see 5% of the universe and 95% they say not, and on the other hand they say the universe is 13.75 billion years old, plus minus 50 million years, then for me as an experimental physicist, if I only know 5% of my observation, then I would be very careful to make these kind of statements. But I mean, for me it sounds reasonable. I have no reason to really doubt it. But also I would not have sort of the instruments to say, okay, what are we doing with this? How can we sort of make it plausible that this is really a correct result, or there might be something wrong with it? So how can we operationalize this in terms of saying, okay, this would be a way to proceed with this kind of information and to make something better out of it, or to believe in it and say, okay, this is true.
Mm-hmm. Yeah, I'm with you, of course. I also follow the measurements of these Hubble constant, but I mean, I think they are claiming too many digits of the age of the universe, but that's not really the basic problem. The basic problem is that there are lots of things that do not fit, and they are inventing more and more parameters, not only the Hubble constant, but also the reionization temperature and the galaxy bias, because we can explain the structure and. Mike Disney, a very well-known, a very experienced astronomer, he counted 73 parameters in cosmology. So I think this is not the fault of particle physics. This is not the fault of the cosmologies. It's an inherent, maybe inevitable structure that science follows.
Okay, but that's a problem, yeah.
Yeah.
So there's no solution to this.
Well, I think there could be a solution in terms of, well, looking at history first, having some more doubts, not be as convinced as we sometimes are, and really go to the raw data. I think this is a good idea. You might appreciate as an experimentalist.
Yeah. So would you say, from your experience, there are sort of soft indicators that there are too many parameters and there should be a revolution in this area, or would you say you can be comfortable with it?
I think there is a hard indicator. It's geocentric astronomy. This is a hard indicator. They had lots of parameters too. Yeah.
Final comment, please, brief.
Just one short comment again. You mentioned Gargamel. When I was a young student, we had the original films of Gargamel in our institutes, and there were women there who were educated to measure them. We have master classes at LHC at CERN now. Any student or any pupil in Germany can go to these master classes and do the data analysis themselves. We teach the students how to do that, just that they get an impression of it. Mm-hmm. The main problem I have is, in your arguments, is that you, to my mind, you want to live in a kind of Disney world which is simple. Yeah? If you do solid state physics, you have so many experiments and so many data, you cannot put it down to 5 parameters, all the solid state physics of all people. Yeah? In the same way, the particle physics is at a level nowadays that you have a complex and huge amount of data available, and we have some kind of theory which has never been tested false. And it works for hundreds of results. Yeah? And it's wrong to say, don't believe those people, our world is a Disney world, it's simple, it has to have only 3 parameters. Yeah? That is the wrong approach. It's especially dangerous because there are so many people, especially in the US now, who don't believe in science anymore and who don't believe in anything that the scientists do. And the way you argue goes also in this direction, to my mind, or it helps those people to come out.
Well, I mean, it doesn't help to compare this to some nonsense of intelligent design or something. Just if somebody doubts, okay. And there is nothing special in the fact that you're, of course, teaching your traditions and your practices to students. Okay, this is also quite normal. I just would ask if you have read the book by Andrew Pickering, but I think the very basic mistake you're making is that so okay, nature is like that. It provides us with 200 parameters, so we have to work on it. You make these comparisons with solid state physics, or once I heard a particle physicist who compared it to architecture. He said architecture is so wonderfully structured and ornamented, but we are not talking about fundamental physics. Okay, Dirac, Einstein, all these people who really have found out something, they were convinced that a good theory has to have few parameters. Dirac worried all his life because he just couldn't explain the ratio of electrons and protons. He would be just sick of this approach. Okay, and this has to be said. This is very, very different from the physics of the beginning of the 20th century. Was what you're doing. It's very, very different. That's all what I have to say.
We're going to resolve the discussion today. Thank you again for the provocative talk. Thank you for the controversial discussion.